So now you know what the null space is, but you still don't know why it is so important. So let me try to explain it to you here. So the null space is useful when you are trying to solve the system A times X equals B. So let's say I give you, given a transformation A and a vector B, I ask AX equals B, find X. Okay, I ask you this. So two things can happen. If the determinant of A is different to 0, then you can calculate the inverse of A. And then you can say X equals the inverse multiplied times V. Right? And that makes perfect sense because you have your input space, you know what V is, and you know that X takes you to V if you apply the transformation A. But the inverse transformation brings you back from V to X. Yeah? So this is very simple answer, very easy. But what if the determinant of A is 0? There is no inverse. So then, if I ask you what is X, find X, you would be tempted to answer that there is no answer because there is no inverse, so you cannot go back. But that wouldn't be a complete honest answer. Why not? Because actually there can be infinite values of vector X that end up in V, as you saw. So when the determinant is 0, you know that for every output vector V, there is a subspace of vectors that end up in V when applying transformation A. Yeah. Therefore, if you are really interested in knowing the answer to the problem A times X equals V, what you should do is you should be giving me the entire subspace. So you should say that X equals a subspace. And you should give me which subspace this is. How would you do it? So the null space would be very useful for doing this. Let me explain. Imagine that you manage to find one possible vector inside this subspace. So let's call this vector x0. Let me erase the orange curves. So imagine that you find a vector x0 which maps onto V. Okay? But that's not enough. That's only one vector among an infinite subspace of vectors that would fulfill this equation. Yeah? So what you can do is the following. You can say, okay, the general solution for X is equal to the solution that you found, this particular solution, x0, plus the null space of A. Remember, the null space of A is a subspace. For example, in the previous example, it was a line. It was the y-axis. Yeah. So in that case, you would say that any solution of X, you can add to it any vector within the y-axis, and it would still be a solution. Proof of this is very simple. So we want to prove that if x0 is a solution to this problem, A times x0 equals V, then x0 plus null space of A is also a solution. So how do we prove this? Well, you calculate A times the new solution, x0 plus null space of A, and then you apply linearity to this, yeah? So this is equal to A times x0 plus A times the null space of A. And then we know that A times x0 equals V because it was one particular solution. And we know that A times the null space of A, so null space of A is any vector within the null space. We know that A times those vectors is equal to 0 because that's the definition of null space. So you get V plus 0, which equals V. So we have proven that A of x0 plus the null space of A is a solution to the problem Ax equals B. So that's the way in which you can know the general solution that I'm asking you for. Yeah. So remember, I was asking you, given A and V, find X. So if the determinant of A is not 0, you find the inverse and you give me a single vector X. But if the determinant of A equals 0, then what you have to do is you have to find a particular solution, and we will see how to do this, but that's very, very easy. And then you just find the null space of A and you add them up. And that will be the general solution that you can give me. Okay? So we are going to see an example of this. Thank you for watching.